Okay, so I can make this tape go around my head. I can make it go in a circle, and that's because I'm exerting a centripetal force with a string. If I had sufficient mass, though, and it would be a lot of mass, I could actually make this thing go around because I could exert a force of gravity on that roll of tape that would make it go in a circle. Okay, but I'd have to have a lot of mass to do that. I'm not even close. As you could imagine, that force of gravity is actually astonishingly small, even though I weigh considerably more than a stapler, and this is about like a pen or something like that, right? But the force of gravity between the sun and the earth is, of course, what makes the earth go in its path around the sun, right? And the force of gravity between the earth and the moon is what makes the moon go around the earth. And so all we do in these types of problems is we set the centripetal force. These things are centripetal forces, so it's the satellite mass times its velocity divided by r, or the satellite's mass times 4 pi squared r over its period squared, right? Aren't these just centripetal forces? Yes? Okay, we just set the centripetal force equal to the gravitational force. And all we're saying is that the centripetal force comes from gravity. Yes? Does that make sense? So really the physics here of orbit is very simple. The algebra is somewhat more complex, but it's always just like slide the thing around, and then either at some points we have to square root or we have to cube root sometimes, worst case scenario. Sometimes we're done when we slid the stuff around, right? It turns out that's not the hard thing. I've discovered that the hard thing is that people don't know how to type these complex expressions into your calculator. It's something I learned because I was a computer science major and I had to learn that. But you guys are not all that clever yet about that. Some of you are, some of you aren't. So when I show you how to do this with the calculator, make sure you pay careful attention. I've already talked about like how you deal with a numerator with 2 factors. That's why, right? This is stuff that we got to learn how to do. But write that down in your notes. Those are the 2 orbital conditions. And let's solve, I'm going to solve 2 example problems, and I'll show you how I think you should do it. And then we'll have you guys try your own. Okay? So the first one is the space station, the International Space Station, actually varies quite a bit in its height above the Earth. It is not actually all the way above the atmosphere. The Earth's atmosphere does not just like end at a particular spot. It just gets thinner and thinner and thinner as you go out. And so it's actually close enough to the Earth that there's a little bit of drag from the atmosphere that slows it down, and it spirals its way toward the Earth. And then every now and then a space shuttle or something gets up there and pushes it, speeds it up, and it spirals its way out, right? And the reason they don't put it very, very far into space is that it would then be too difficult to get to. If you put it like way out by the moon or something like that, right? Okay, so it is actually 250 miles above the Earth. Now, here is the Earth. Connor, catch. He's got the whole world in his hands. Oh, here, no, toss it back. This is like very, very risky to throw. This is my globe. I bought this because we talk about orbit. This one's got the Union of Soviet Socialist Republics on it, right? Which makes this just really precious. But that's the general rule. If you buy a globe, okay, it is guaranteed that some country somewhere on that globe will have just recently changed its name. Okay, this happened in, the 90s or something like that, so there's really no good excuse. But I just think that's funny. Okay, now, the diameter of this thing is about 8,000 miles. Its radius is about 4,000 miles, a little bit less. Okay, this is 4,000 miles. That means that 250 miles would be, well, a quarter of a quarter. That'd be 1/16 of a radius above the Earth. That is about, the space station is about here, isn't it? Something like that, right? It's very close to the Earth, isn't it? When they look at the Earth, it's like, ooh, that's a big Earth. You can see that it's curved from here, but it's big. If you look in that direction, that's pretty much what you see there, right? Okay, so yeah, I mean, you could do that, right? This is, there we have it, right? Okay, now, 2 reasons why we can't use 250. Reason 1, it's in miles and we got to use meters. Reason number 2, yes, sir? Needs to be from the center of the Earth. This is very good. Okay, so let's draw a little picture of this. Here is the Earth. This is amazing. Here is the space station. I've exaggerated. It's, oh my God, 2 concentric circles. So this distance is 250 miles, right? This distance is about 4,000 miles. Okay? And so obviously what we really want to use is we want to use the radius of the Earth plus how far above. So whenever they give you above the surface of a planet and you're doing anything with circular motion, you almost certainly want the actual radius of the circle or the center to center distance. Okay? And so the first thing you're going to do, and I just did this in meters, there's the Earth's radius is 6.38 times 10 to the 6th, and then I added 250 miles and I converted miles into meters, right? And 1 mile is actually not 1,600 meters as track and field people would have you think. It's not 4 laps, it's 4 laps plus 9 meters and I think some change or something like that, right? So if you really want to run a mile on the track, just go a little farther than 4 laps, right? But it's, there it is, right? So our radius that we're going to use for this thing is 6, whoops, where'd that capital R come from? I don't know. Okay, is 6.78, what is it, 2250 times 10 to the 6th meters. Is that what it is? Yeah, there it is, right? Okay. And then which one of those orbit conditions do we want to use? The top one or the bottom one? And how do you know? Well, I'll give you this clue. If you're dealing with velocity, you want the top one. If you're dealing with period, use the bottom one. We want the velocity, so we're going to use the top one. Very clever. Okay? So we set this thing, we go mass of the satellite, velocity squared over r, right, equals g, mass of the central body, mass of the satellite over r squared. Now, are these radii the same? Is the center to center distance the same as the radius of the circle the satellite goes around? They are the same if the Earth does not move. Now, when would the Earth move? Well, the Earth would move if the satellite had a mass close to the mass of Earth. Wouldn't it move? In fact, if they had the same mass, if you had a binary star system and they had the same mass, about which point would they orbit? They can orbit each other. They'd actually orbit around their center, and so the center to center mass would actually be twice the radius of the circle or something like that, wouldn't they? Yeah? Okay? So this is a failure of our assumption here. This orbital condition only works when the mass of the satellite is much, much smaller than the central body mass, as is true for any satellite that we launch. It's not exactly true for the moon. The moon is actually about 1/100th the mass, a little more than 1/100th the mass of the Earth. And so the Earth actually moves a little bit around the moon. The moon mostly moves around the Earth, but the Earth moves a little bit around the moon, which is sort of weird. The Earth is actually going in a little wobble. As the moon goes around it, it's kind of like a heavy dance partner dancing with a light dance partner, and they're doing one of those river dance spins, right? The heavy person tends to not move much, and the light person moves a lot, right? Okay, the Earth actually does a little kind of like this, right? This is why there's actually 2 tides in a day, okay? Because there's a bulge of water toward the moon, and then there's a bulge on the other side of the Earth because the Earth is moving. Yeah? Isn't that crazy? And then, of course, while the moon is going around the Earth is, of course, rotating like crazy, right? 27 times for every time or something like that the moon goes around, right? And so that's why we get tide and then tide every day, right? Something like that, right? Okay. Okay, so now back to here. Okay, and then there's also some confusion. Kids always have a confusion about which mass do we cancel, because I could give you the satellite mass. Here I didn't give it to you, so it's obvious that we must use the Earth's mass, right? Why is it that the satellite mass cancels? Why is it the satellite mass times v squared over r? Is it because the satellite is the one that's actually moving at the velocity in a radius circle like that, yeah? And the Earth is, we're assuming, doesn't move, is why this works, right? So that's why we can cancel the satellite mass, okay? And we don't even know it, we don't need to know it. This is good news for astronauts. If you step out of your ship, your spaceship, you will have the same orbital radius as your ship, because your mass, the mass of whatever the thing is that is in orbit, doesn't matter, okay? And then now let's solve this for v. How hard is that? Well, I move that r up there and it's going to cancel one of those, isn't it? Yeah? It goes away. And then I'm almost done. What do I do? I just got to square root both sides, right? So v is going to be the square root of